You've probably done this without thinking twice. You grab an ice cube from the freezer, maybe to cool a drink, maybe just because it's hot outside, and you hold it in your palm a little too long. At first, it's just cold. Then, somewhere around the 20 or 30-second mark, something strange happens. The sensation stops feeling like cold at all. It starts to feel like fire. Most people assume this is just a figure of speech. It burned so bad it was cold, we say, treating it like an exaggeration, a poetic way of describing something uncomfortable. That's what everyone assumes. But that's not actually true. Ice doesn't just feel like a burn. In a very real, measurable way, it can cause the same kind of tissue damage a burn does. Your nervous system isn't exaggerating when it screams burning at you. It's reporting something closer to the truth than you'd expect. So what is actually happening under your skin when something gets cold enough to hurt? To understand that, you have to throw out the idea that heat and cold are opposites your body treats differently. At the sensory level, they're shockingly similar. Deep in your skin are microscopic protein structures called nociceptors, tiny sensors whose entire job is detecting potential damage. Some of them respond to intense heat. That's simple enough. But here's where things get interesting. Several of the exact same receptor types that fire when you touch a hot stove will also fire when your skin gets dangerously cold. One well-studied receptor, TRPV1, is famous for detecting heat above roughly 43 degrees Celsius. It's also been shown, under certain conditions, to respond to extreme cold as well. Your body, in other words, sometimes uses overlapping wiring for two sensations that seem like total opposites. Which raises an obvious question. Why would evolution build a system this sloppy? The real answer is surprisingly different. It isn't sloppiness at all. It's efficiency. From your brain's perspective, heat and cold aren't really the point. Tissue damage is the point. Whether your cells are being cooked or frozen, the end result is the same category of emergency: cellular injury. So instead of building entirely separate alarm systems for every possible threat, your body reuses circuitry. It's like a single fire alarm wired to detect both smoke and flooding, because in both cases, the building is in trouble. Efficient. Just occasionally confusing. That overlap explains why extreme cold can register as pain almost identical to heat. But it doesn't explain why ice can leave actual damage behind, not just an uncomfortable sensation. That part of the story starts with your blood vessels. The moment your skin senses dangerous cold, your body makes a decision that seems almost self-destructive. It clamps down on blood flow to that area through a process called vasoconstriction. Blood vessels near the surface narrow dramatically, redirecting blood toward your core. This is your body protecting its most vital organs at the expense of your fingertips, your ears, your nose. Sensible from a survival standpoint. Rough if you're the fingertip. With less blood flow, that patch of skin loses its main defense against cold: warmth delivery. Temperature drops further. And this is where things stop being just uncomfortable and start becoming dangerous. Here's the part almost nobody expects. If skin gets cold enough for long enough, actual ice crystals can begin forming inside and between your cells. Not metaphorically. It's literally. Water inside living tissue doesn't behave like water in a glass. When it freezes inside a cell, the expanding ice crystals can physically rupture the cell membrane, like tiny shards puncturing a water balloon from the inside. Multiply that by millions of cells, and you get real measurable tissue injury. This is frostbite. And at a cellular level, it causes destruction that looks remarkably similar to what happens with a severe heat burn. Cell membranes rupture. Proteins denature. Tissue can die. This is why doctors classify frostbite in degrees, 1st through 4th, using almost the exact same severity framework used for thermal burns. Redness and numbness. Blistering. Deeper tissue involvement. In the worst cases, tissue death requiring amputation. The label is different. The underlying devastation is eerily parallel, so the sensation isn't lying to you. When ice held too long against skin feels like fire, your nervous system is reporting something biologically accurate. Damage is happening. This is also why something called an ice burn is a real medical term, not just casual slang. Athletes using ice packs incorrectly, people using cryotherapy without proper protection, even babies left with an ice pack against bare skin for too long, all of them can develop injuries that look on skin almost identical to a heat burn. Redness, blistering, peeling. The mechanism was cold, but the damage reads like fire. There's something almost poetic about this, though biology rarely intends poetry. Your body evolved in environments where extreme heat and extreme cold were both constant threats to survival. Rather than building two completely separate warning systems, it built one unified message. Something is wrong here, stop what you're doing. The specific temperature causing the damage was almost secondary information. The priority was speed of response, not precision of description, which, admittedly, is a little unfair to your fingertips in the moment, but remarkably clever from a survival standpoint. But this shared wiring between heat and cold goes even deeper than most people realize, and it explains a few other strange sensations you probably felt without ever connecting them to this. Have you ever noticed that extremely spicy food and extremely cold ice cream can sometimes trigger a weirdly similar kind of intensity just before the actual pain sets in? That's not a coincidence. Capsaicin, the compound that makes chili peppers spicy, activates that same TRPV1 receptor we mentioned earlier, the one built to detect heat. Your brain interprets that chemical signal as literal heat, even though nothing hot has touched your tongue. It's an illusion built entirely on borrowed circuitry. Meanwhile, menthol, the compound in mint, activates a related receptor called TRPM8, which is normally triggered by cold. That's why mint feels cool even at room temperature. Your nervous system isn't measuring actual temperature in either case. It's reading chemical keys that happen to fit locks originally designed for thermal danger. Which means the burn from ice and the burn from a chili pepper aren't just similes anymore. On a neurological level, they're closer to cousins than metaphors. This shared circuitry also explains a phenomenon researchers call paradoxical heat sensation. If you press something cold enough against skin in just the right way, some people briefly feel a jolt of heat instead of cold, especially in patients with certain nerve conditions. The wiring gets crossed for a fraction of a second, and warmth signals fire, even though nothing warm is present at all. It's a strange reminder that what you feel isn't a direct readout of the physical world. It's your brain's best interpretation of overlapping, sometimes glitchy signals. Historically, this confusion cost people dearly before science understood it. Arctic explorers in the 19th century often described frostbitten limbs as feeling like they were on fire moments before numbness set in, and many misinterpreted that sensation as a sign their extremities were somehow still safe, since burning didn't fit their mental model of freezing to death. That misunderstanding delayed treatment in documented expeditions, turning survivable frostbite into permanent tissue loss. Understanding that cold and heat share a warning language isn't just a fun fact. It's the difference between recognizing an emergency and dismissing it. There's one more twist worth mentioning. Because this pain response is tied to nerve signaling rather than a simple thermometer reading, individual sensitivity varies enormously. Some people can hold ice far longer before the burning sensation kicks in. Others feel it almost immediately. Certain nerve conditions, poor circulation, even prior cold exposure can all shift when that alarm gets triggered. Your ice holding tolerance isn't really about toughness. It's about how your particular wiring reports emergencies. So the next time you're holding a piece of ice and that first sting starts creeping in, you're not imagining a connection between fire and frost. Your nervous system already knows there isn't much of a difference between the two. Both represent one thing to your cells. The world has become inhospitable and something needs to change right now. The ice was never harmless. It was simply cold enough to convince your body it was on fire.